Now here's the weird fact. Anytime you're given a single vector like v, it actually represents infinity vectors. What do you mean? This vector right here is just one vector. How could that one vector represent infinity vectors? It does. It represents every single vector that has that exact magnitude, length, and any vector that shares the direction that it's pointing, which is kind of upwards and to the right. And you may think that this key weird fact has no bearing on you, but today you're going to see that it will matter. And in physics, it matters too. And the reason why is it means that anytime we're given a vector, as long as we maintain its integrity, how long it is and where it's pointing, you can move it around anywhere you need to help you out. And that's cool, because sometimes if you're trying to work with a vector diagram and you've got more than one vector in your picture, you can move your vectors around as long as when you translate them, they stay the same length and they stay pointing in the same direction. Very, very powerful fact. Super powerful. Okay. So, any questions so far?
Nope.
Okay, we're all good. Yay. Okay. Let's talk about some more definitions. I know there's a lot of definitions to start us off. We can't do a lot of fun until we lay down all the groundwork so we can play a good game, right? You got to know the ground rules for the game before you play. Standard position. What does that mean when you have standard position of a vector? The standard position means the initial point, that's the point that doesn't have an arrow on it, is located at the blank. At the blank? What's that? And that is at the origin. So if your vector is in standard position, somebody has moved it around so the initial point is there at the origin. And that's really useful a lot of times when your vector is located in standard position. Does it have to be? No, but it's easier to work with, as we'll soon find out. All right, now let's talk about the definition of component form for a vector in the plane. So remember, plane means not an airplane, but it means 2D. If a vector v is in standard position, then the vector v can be written like that. What? Okay, you've got these angular brackets like this, and you're going to be drawing angular brackets on your handwritten work, and then two numbers separated by a comma inside of the angular brackets. Now those two numbers, they're just going to be pure numbers, are known as the, quote, scalar components of the vector v. And remember, we just talked about what a scalar is. A scalar is a pure real number. So the numbers that you see inside your angular brackets are just pure real numbers delimited by a comma. Okay. And this is known as component form. I love component form. It's my personal preference. There is another way to denote a vector, but we're not going to do that right now. I'm hoping we can get to it today. We'll see about the time. Okay, and the other way is the way our physics brethren like to use better. So if you have a physics textbook already, it's very rare that they use component form, which is unfortunate. You'll see why I'm not a big fan of the alternative form sometime this week, but I can't tell you yet. Hang in there. The zero vector, is there such a thing? We denote it with the number 0 with a little arrow on top. That's to distinguish it from the scalar 0. Those are two different things. The vector 0 looks like that. If you're going to denote the vector zero vector in component form, you'll use those angular brackets and then put 0, 0, because the scalar components for the 0 vector are zeros. Yep. Now, what do you think is the magnitude of the 0 vector? And what would it even look like? It'll look like just a dot. So the 0 vector, if you draw a picture of it, it doesn't look like a directed line segment. because it has zero magnitude. It's zero length. So I know it kind of looks funny. A zero vector just looks like a dot. Well, what about the arrow? I thought you said that a vector looks like a directed line segment. You know, it's got an initial point and another point with an arrow. Yes, it's true. Other non-zero vectors look like that, but the zero vector is a dot. So what is its direction? And don't say zero. I know this is weird. It actually is assumed to point everywhere. It points in all directions. That's strange. I know. I don't make this stuff up, folks. I just report it. Yeah, I know. Okay, let's look at how to find the magnitude. Super easy because it's just the result of the Pythagorean theorem. You've heard of the Pythagorean theorem, right? So if somebody gives you a vector in component form, then the magnitude, which is sometimes called the length, is denoted with double bars on either side of the vector. Although Briggs, your textbook, uses single bars, which I'm not a big fan of because some people think that looks like absolute value, and magnitude is not absolute value. So I personally am not going to be using the single bars in lecture, and I really am hoping you'll warm my heart if in your handwritten work you use double bars also. Different textbooks use different notation, but I'm old school and I learned with the double bars. I prefer it. Okay, so how do you get your magnitude? You simply take the square root of the sum of the squares of your scalar components. And we're going to do some examples here in a moment with actual numbers, so don't worry. Okay, now, there is a difference between a geometric vector and an algebraic vector. Well, what is the difference? I'm going to get to it in a moment with the next example. So don't worry, we're coming there. So we're going to do a lot in this next example. Are you ready? Because it'll be similar to what I'll put on a quiz this coming weekend. And it's easy, you'll love it. Suppose somebody gave you the initial point of your vector and they said, oh, it's point P, X1, Y1. You know, so let's just say, I'm just going to draw something here. Here's P, X1, Y1. Fine. And way over here is Q with some other coordinates, X2, Y2. Fine. Okay, let's say somebody wanted you to find the vector PQ. So if I draw PQ, the terminal point has the arrow on it. There's the vector PQ right there. How would you put this vector into standard position? So what does that mean? It means you're going to take this vector PQ and translate it so that you move it where you maintain its integrity. And when I say maintain its integrity, what that means is you still want it pointing in the same direction and you still want it to have the same magnitude. So I'm going to say, if I move it, your PQ, where the P is located here at 0, 0, and the Q is over here, what would be the new coordinates? We already know what the new coordinates of P are. It's obvious, 0, 0. But what are the new coordinates for the Q? What are his coordinates? Because he got moved. Well, the formulas are right here. Okay, X can be found by taking the difference of the X coordinates of P and Q, and order matters. You want to do terminal minus initial. So the terminal X coordinate minus the initial, and then the new Y coordinate is terminal minus initial. Now the vector PQ, if you're going to denote it in component form, you use these angular brackets, and the X and Y, which you just found with these formulas, which are the same new coordinates of Q, are the scalar components of PQ. Okay, so we're going to do a full-blown example right now with all the new notation and these new formulas we just learned and everything. And hopefully after I get done with this example, some of the fog will lift for you. Yeah, check it out. So A, let's graph it. 8, -3. It's right about there. Here's the point 8, -3 on this graph, and we'll call him A. And then B is the point 4, 5. 4, 5, right there. There's B. And they want us to give the component form of AB. So the vector AB looks like this. And it is known as the geometric vector. Write this down, it'll become clear in a moment. So that's the vector AB. And it looks like it's kind of pointing up and to the left a little bit. Fine. Okay. So in letter B, they want us to find the magnitude, but I don't want to find the magnitude just yet. Well, why not? Because I want to do another step first. What I'd like to do is I want to translate this vector so it is in standard position. What does that mean? That means that A is going to get moved to 0, 0 by default. We're going to move them over there. That's the new A position, because the standard position, the initial point, is located at the 0, 0. Now, where is B going to go? You know, when we move him, well, he's going to be somewhere out here, but I want to know exactly. Don't eyeball it and guess. So B, his new coordinates are, if you follow the formula we just said, his new X is going to be his old X minus the initial point's X coordinate, which is -4. And then the Y coordinate will be found by taking B's Y coordinate, which is a 5, and subtracting A's Y coordinate, which was a -3. But 5 minus a -3 is 8. So the new coordinates for B, when you move him, are going to be -4, 8. So if I graph that, that looks like it's going to be, where the heck is it? Like right there. -4, 8 is the new B. And there's our vector. Ooh, okay. Notice that this new vector is now in standard position. We call this standard position when the initial point is located at 0, 0. And it's also known as an algebraic vector. It's algebraic once you've moved it over into the standard position, as opposed to being a geometric vector somewhere, you know, located just sort of out there, but not in standard position. Now, how do you denote AB now? Because now we can do letter A. I'm going to use angular brackets, and you're going to use these new coordinates that you found for B, but you're going to put them inside angular brackets. So this right here, AB in component form, you got the angular brackets, and then the scalar components are -4 and +8. Okay, and now we can find the magnitude. So for letter B, we want the magnitude of AB, and that is going to be the square root of the sum of the squares of the components. And anytime you square a negative, I hope you remember it's positive. So you don't even have to put -4 squared. You could have just put 4 squared, right? So what does this end up being? So I'm going to ask you guys a question. True or false? Is it legal to do this as my next step?
No, that's
No.
illegal.
Good. Yeah, you can't do that. That's not mathematically correct. So don't do that. Although I do see some students, when they get nervous on a test, they do silly mistakes like that. So that was false. Okay, you're not allowed to distribute a radical over a sum. Oops. What happened there? Oh, sometimes okay. So this is, instead, you're going to actually add 16 and 64 together, and I get 80. I'm going to take 1 point away from you if you leave it as square root of 80. Well, how come? MyLab Math will probably give you full credit, although it probably depends. The reason why I would take off 1 point for this problem is because 80 has some factors that are perfect squares. You can simplify this radical just a little bit. So what do you mean? Well, 80 can be written as 16 times 5. Yeah. And since square root of 16 is 4, you can simplify this radical. So there's the magnitude, 4 square root of 5. And please note that magnitude is a scalar. That's right, because it's a length. So it's a scalar quantity. So we're done with letter B, and that is the length of the vector AB. And in part C, they wanted us to sketch both the geometric and algebraic vectors on the same graph, but I claim I already did. Aha! And we're done with example 1.